let's start discussion series on electricity and magnetism. This is part 1 of our discussion series on electricity and magnetism. We will be using the Griffiths book. I know if you're on Twitch, I've already said all this, but this is for the YouTubers. So yeah, if you're following along on YouTube, that's what we're going to be doing. We're going to be using the Griffiths textbook. I will be updating on what pages we're going to be doing and putting my notes on Discord. So if you're in Twitch chat, !Discord. If you're on YouTube, check the description below for that information there. And I do put all of my notes there, so if you don't have Griffiths and you just want to follow along my notes, you're welcome to do that too. But I think on this first day, so let's see, we're going to be doing discussion. Did I spell that wrong? I don't want to talk about it if I did. Discussion series. It just looks weird to me. Part 1. And I think we want the overall goal of this is to derive and understand the Maxwell's equations. So Maxwell's. And today we're going to see the first one, right? So let's lay out the Maxwell's equations first so that we have them and we've seen them. I'm just going to do the differential form of the Maxwell's equations. So it's the gradient, which is basically like the derivative in all directions, of the electric field is equal to the volume density over the vacuum permittivity of space. The vacuum of permittivity of space meaning basically how well the electric field will move in space. Okay? Now it's something kind of interesting to know that when Maxwell was coming up with this stuff, he had the vacuum permittivity of space was, you know, how the electric field moved in space and how charges moved in space and everything like that. And it wasn't actually for space. Does anyone know what it was for? Because we call it space now, but that was not how he originally described the theory. So the next one is the curl of the electric field, which curl and gradient work a little differently. Of the change of the magnetic field with respect to time. Next up is the gradient of the magnetic field is always equal to 0. And we'll see a couple different forms of these eventually. But these are the basic forms that you'll find in the cover of Griffiths. Ether, very good, yeah. Very good, yeah, ether. But that's what it was for, because when Maxwell was writing these, he was under the impression that there was an ether. So the permittivity of the electric field, it was actually something that was propagating through the ether. And it wasn't until Einstein came along and was like, hey, that's not a real thing. Anyways, let's keep going. So now we have the Maxwell's equations. So the goal, again, is to derive these and figure out how to use them, right? Understand them. We want to, permittivity of free space sounds cooler. Yeah, definitely. Than of the ether. Definitely. So these are not in the notes, but let's begin the notes now. This is the overall goal of the discussion series, okay? So what are we going to do today? Well, we're going to talk about electrostatics.
Things get a little bit weird.
Dananas, thank you for the follow. Welcome to the channel. Electrostatics. Let's do it. I just drew the same derpy looking R. Oh well. So what's a charge? A source charge. I think these are good questions. I would like to see some answers. So while I write out some questions, start preparing your answers. What is a charge, and how do we know charges exist? Those are two questions right there. What is a charge, and how do we know it exists? Not what is a particle, right? Not what is a particle, but what is a charge? An electric charge is a measured amount of magnetism in motion. Interesting. So you're kind of going the other way. You're kind of going with what it is with magnetism, right? So here's the deal. I don't really think anybody has a good idea what a charge is fundamentally.
Yeah, people who
right?
troll the stream are awful people.
A charge is a property that a particle possesses which distinguishes from other particles to its charge. Very good. So that's exactly what I was going to say. I don't think anybody knows what charge really is, okay? But we do know that particles have charge. And how do we know it exists? How do we know it exists? That's the next question. These questions are too hard, Lobo. They're riveting. Come on. AFK for a bit, sure thing. Forces, exactly, Dodo. Very good. We know charges exist. So what is a charge? No. No. That's my spelling of but we do know it exists because
Welcome to the channel. Things get a
we
little
see
bit weird.
a degree of freedom for which particles interact. I just made that up on the fly. It's not in the notes. I would have wrote it down if I thought of it earlier. But we see a degree of freedom.
Because you can shock yourself opening a lighter.
Yes. We do know charge exists because we can shock ourselves with piezoelectric crystals on accident. What is gravity level of drawing? Yes, it is in fact that, exactly. But no, it's true because we can see a degree of freedom for which particles interact. But that's about it, right? Like we know that particles interact. We see it in the magnetic forces, right? Like magnets, they repel. And then you can do the same thing with electric forces. The voltage difference that we see, especially like when we get out the Tesla coil, you know, when we're doing we'll do that, we'll bring the Tesla coil out for E&M much later. When we get to like magnetic fields and whatnot. But yeah, like you can see a potential difference between the two. We know that there's something separating the two, and then you can strip the electrons out of the air via, you know, the potential difference across two charged objects, right? And that is how we know that charge exists. We see the interactions happen. We know we can describe a degree of freedom to particles to which they interact. Okay? So let's go over some of these properties that they have before we start to get into it. Namely, the property of superposition. Kind of the property of superposition is as the notes say, I'll just read from it. An interaction between any two particles is completely unaffected. So now we're going to talk kind of strictly about particles for the first part of this, and then we'll get into objects. But for now, let's stick with particles. So we just have particles and the superposition of charges, interactions between any two particles. An interaction between any two particles is completely unaffected by the presence of other particles. And then on top of that, another little tidbit that I added was, what does it mean though for which particles interact? Oh, like for example, like I said, the Tesla coil, like having the potential difference, or lightning. Lightning works just as well, right? The potential difference between the charged particles in the clouds and the charged particles on the ground, right? And then boom, lightning, right? That's an interaction. That's a lot of interaction. Many, many interactions. And so we can ascribe some charged particles to that situation, and everything works out nicely. So then the tidbit that I added is for the superposition definition is the total interaction between all particles is the sum of the individual interactions. That old shtick. So let's kind of draw some pictures. Griffiths is incredibly picture heavy, which is one of the reasons why I actually didn't like him the first time I read it, but it's grown on me significantly since then. So we're going to have some different things, and we're going to label them to start. We're going to have this Q here be the source charge. There's going to be a main difference between a source charge and a test charge, which is this Q up here. And then this is just going to be the distance between the two. Okay? Now, if you're following the notes, what do you call it? Oh, jeez. Oh, jeez. Griffiths, yo! Exactly the Helen. That's what we're doing. He's got this R, this cursive R, so we're going to roll with it. Not a huge fan of some of the variables he chose either, but I'm going to get off my high horse here. Griffiths is a great book. We going to roll with it. So, and I think the more you use it, the more comfortable you get with it, for sure. But so this is just some definition, just some labeling of stuff. We have Q, the test charge. The capital Q is the test charge. Lowercase q is the source charge, and the distance is r. Cursive r. Now, another thing is that we can think of the electric field, and we'll talk more about this in a little bit. But it comes radiating off in all of the different directions. And the only reason I'm drawing it now instead of waiting until Griffiths gets to it is to kind of take care of what r hat is, because eventually we'll need r hat. R hat is basically the direction of one of these radially. So take a circle. Anything away from the circle, do I have one? I do have a circle.
Follow the notes without a hieroglyphics degree.
Always, always. Recycled jokes. I see that's what we've come down to, huh? So if we have a sphere, right, radially is just direct outward in any direction. Let me get a little closer. You can't focus, I know. The camera. I'm talking to the camera. But radially outward is radially is in any direction away from the surface or from the inside or from the the center of the sphere. That's what radial direction means. So we're going to be doing a lot of swapping coordinates and everything like that, so we'll have to be careful about that, but r is just the radial direction. So, let's see here. So first up, we're going to start with our first named law. A lot of these things have names. A lot of these laws have names, and so we're going to try to keep them associated with the right name. The first one up is Coulomb. Coulomb's force law. Coulomb's law. And it's written like this. It's the force of a particle on another particle, or I should say the force of the source charge on the test charge. Now, Griffiths kind of like, if you ask Griffiths, what's the mechanism for the force? He kind of just says this is kind of due to the experiments. The answer is based on experiments, which is another reason why I had trouble with it. The Sharp Spoon, thank you for the follow. I think I missed that. Thank you for the follow. Welcome to the channel. The Sharp Spoon. Nice. Yeah, so Coulomb's law is just this, and he basically just says, it's experimental things. But you can get to it through other various ways. We're not going to worry about that. Maybe in the future, not a discussion series episode, but in a future just part on stream, if you guys are interested, hop into Discord, let me know that you would like to see the force derived out of I don't know, something else, and we'll try to do that for sure. But then let's also do one more thing. Let's kind of talk about this crazy R. The crazy R is a vector subtraction because we really want to start at some origin, right? So if we want to have this be the origin and this be our source charge and this be our test charge, we want to talk about, vectors like this, where this is r prime, this is r. And then, of course, this force right here only has to do with these charges. It doesn't really have to do with the origin. So we want a distance going from one to the other, and that's where this crazy r comes from, okay? So crazy r is the difference between the two, and that's what crazy r is. Now, let's write that out, though, so you guys can see it. Is equal to r, I think it's, r minus r prime. Where r is the distance from...
Why is the r crazy?
Why? For the same reason you're crazy. Nobody knows. All right, next up. So we can write this law of superposition. Let's do that really quick. So the law of superposition, again, like I said, is that the interactions between two source particle and a test particle are independent of any other interactions between any other sources and test particles. So that if we wanted to say, hey, what's the combination force between all of the sources, all of the forces and all of the tests, is we can just add them up, all of the forces individually, right? And that was what I was saying earlier. That does have another form, though. So let's write that out. So we can get on to the next part. La-di-dee, da-da-da-da. La-da-da-da-da-da-da. And basically, this next part is F total is equal to all of the forces summed up. But what do all those forces look like? Well, we can factor out a test charge, because the test charge is going to be in every single one of them. And then we can factor out a 4 pi epsilon naught, because that's going to be in every one of them. But then the only thing left over is going to be all of the individual source charges, the radius away from the source charge. Oh, these are squared, aren't they? Squared. I think in the notes I forgot the squares. So please grab your...
Melko wants to make that crazy r squared linear.
Yeah, so I did drop that squared from each of those terms in the notes, so you might want to add that. But anyways, okay, next up is the direction. Each of them is going to have an associated direction radially away, so we want to make sure that we have each of them having their own separate unit vector, depending on where they are. Squared, crazy r. Sorry, these are supposed to be r hats, not vectors. Those are going to be different in a second, which is just the direction, again, radially away from the source charge. You get the picture. So now we have this thing right here, which is like, okay, whatever, that's a constant, the test charge, right? That's just a test charge and then a bunch of constants on the bottom. But what is this? You know, like, is there something to tell us what that is? Right? It seems that each source charge can have some sort of different influence on the test charge. We should have a name for that. You know? And hence the electric field was born. We call this the electric field. Up from the ashes of this weird equation, the E field is born. But now I got another question for you. What is the E field? What is the E field? So all source charges affect any test charge? Yeah, so you can consider a single, so that's what superposition tells you, while everybody else is typing up their answers to what is the E field. You can consider a single charge, so imagine we had like all of these charges here. So this is Q1, and we could do Q2, Q3, Q4, Q5, Q6. So the idea is that it's fine to ask the question, what is the force on the test charge from Q1? You can calculate that perfectly fine by using this. But then if you say, hey, I kind of would like to know what the force on Q is from all of the charges. Can you do that too? Sure. How about from like the odd?
It is like the force. It surrounds all living matter, Obi-Wan tells me.
So you can use like the odd charges if you want, and then just add up all of the odd charges. You can do the even charges, whatever. Pick your favorite rule. But that's what superposition does. It basically tells you that you can add up the individual components of the forces based off of what charges you're interested in. Okay. So what are we doing now? Yeah. So this is so the question was, what is the E field? Well, again, the E field. Wow, it's hard to read. Hi, BH Blue Raven. How are you? Good to see you. So the question is, what is the E field, right? Well, again, we don't really have like a thing, right? Like we don't have like it's not a fun, like we don't have like a good, like I can't hold it, right? I can't, hug it, which is the same thing as holding it, yeah, I guess. But we know it's there. How do we know it's there? Well, we can see all the interactions, right? You can see particles moving through the E field. Like if you take a particle and you place it in an electric field, it's going to move, right? It's gonna react to the electric field. Not its own electric field, obviously, but another electric field. How do we know that it's going to react to the electric field? Well, because this tells us, right? This tells us there's an electric field associated with this charge and an electric field associated with this charge, right? So the electric fields associated between the two charges are what gives us a force, okay? The force experienced by a unit charge at each position. Very good. Very, very nice. E field is the total area affected by the charges in electricity. You can do a total electric field. There's more than one E field. Yeah, there's an electric field associated with each charge. So the fact that something moves in the electric field is a result. Oh, this is only true if it's plus, by convention. BH Blue Raven, thank you for the follow. Welcome to the channel. So it's by convention, this is plus, so it radiates away. If it was minus, by convention, the arrows point the other way. So then if you have a different charged particle, like say, for instance, if you had a minus q, a minus little q. So if this was big Q, and you had a minus little q, I like to say that the minus little q will ride the electric field lines towards the positive charge, because opposite charges attract, right? So if we had a little q out here, he's a minus, he's q, he's a little q. He's a cutie. I'll stop. He's going to ride the electric lines this way towards the positive charge. Wait, what about the own electric field? Are you sure? Oh, let's not get into that. That's a little bit above where I'm at right now. That's like saying we're going to talk about fringes for, you know, edges of surfaces. We don't do that here, Admiral. Okay, so yeah, so that's what that is, right? So that's what the electric field is. We see the repercussions of it by putting a charge in something. We could hide this charge. Like, we don't need to see that charge there. There's nothing about this that, you know, means anything to us, because if we just set a charge there and it starts moving, we know exactly what to infer about here. That's why the electric field is important. Okay. Your brand. My brand. And then, of course, the electric field. So we talked about this. Good. Check. Now we can say the E field follows the same rules of superposition. So to answer your question more specifically, Ash, yes, the E field, there's more than one E field, and they add up the exact same way where you can add them independently. So if you have many source charges, they're all going to have an electric field. So suppose you knew that there was, oops, that's crazy, R. Suppose you knew that there were, you know, suppose you knew that there were 5 charges, and you knew what the total charge is, 5 source charges, and then the test charge, right? And you can find, you find out that there's a total charge here and this charge, and you find out the total charge, and you find out how many charges you have, and you put a Q here, and you just let it go, let it go, and it immediately starts going towards these charges. Then you can infer some sort of information about what's here, right? Based off of the superposition. They're all going to add together, right? If you know the locations and everything like that of them. So let's do an example. I want to do examples throughout this discussions. Quite a few of them. So let's do an example, okay? So we're on a new example. So we're doing the example. I'm not going to write it all out again. I'll read it, obviously, but you can find my notes on Discord. Grab it in Discord, and yeah. So let me read it, and then we'll go through the example, okay? So first, the example is find the E field, the electric field, at a distance z above the midpoint between 2 equal charges q at a distance d apart. So we want to find the electric field, some distance z above the midpoint between 2 charges, q, and the whole distance between the 2 charges is d, so we'll split it in half, d over 2 for this way, and d over 2 for this one. And so yeah, so there's got to be some electric field. Again, remember, the electric field, this might still work. So remember, the electric field is going to be directly from the source charge, but now we have 2 of them. Oops. Wow. That's pretty bad. There we go. And let's just say there's some theta here. Okay, good. Because we're going to need that. So we have some distance z here, and then d over 2, very good. Okay, so I think we have everything labeled. So let's keep moving. We're going a little too slow. So let's keep moving a little bit. So now we have the 2 electric fields from each of the source charge. We're going to label this E1 and this E2, and they're both going to contribute to some E that's going to be right here. And that E is going to be, so we can write that down, okay? Now here, this is what I always tell my students, is like we have an incredibly powerful, no problem, Tim. We have this very powerful tool in physics, right? Very, very powerful. We use it to get through a lot of tough problems. And this is a tool that you use in this class specifically, in electricity and magnetism when you take it, specifically a lot. And that is the tool of symmetry. Symmetry tells us a very important thing about this, right? Electric field has components. It's vectors, right? It's called spherical cow. We do use that one too much too. But yeah, so this has components, right? The electric field that has components. So we could rewrite each of these vectors like the following. So if this is the point of interest, we have E1 over here. We'll just do E1 because it works the same way. But we have two components, right? We have an X component and a Y component. I don't know why I made them so long. They shouldn't be that long. So we could have this be E1X and this be E1Y, right? So electric fields, vectors, components, okay? And symmetry tells us that these two things are going to have two vectors. Rude. Chegg, that is not the tool. So let's talk about this so we can just say, hey, this is the EZ direction, okay? And symmetry tells us there's going to be a vector in this direction and a vector in this direction that are going to be equal and opposite. Subsequently, thank you, Tyrion, I got to get a drink. Subsequently, they are going to cancel out, which makes it very nice for us because instead of having 1, 2, 3, 4 vectors to add up together, because you have to add up vectors together, you have to add them up each one, Instead of having to add up 4 vectors, we now need to only add up 2. Subsequently, we know that this vector in the y direction is the same for both of these, right? So really, we just have to multiply one of those vectors. We really only need this guy right here. We'll multiply it by 2, and then we get all of the contributions to this electric field. So we'll have 2.
You can write the vectors and watch them cancel out.
Yes. Or you can just cancel them out in your head. Which is what we did. Which is what I did. You can absolutely write them all out and watch them cancel. And then the E field is just going to be 2 times the last component, which is going to be 1 over 4 pi epsilon naught. And it's the Z component, so you're going to need to use a little trigonometry and find out that it's just cosine of theta. Okay? That's the component for the Z directions. Now, this is not fully satisfying because we still have some stuff to get rid of in this equation. Remember, this is the electric field. Luckily for us, there's only 2 of these. And like I said, we're just canceling them away. So this is where we're getting all this from. But we still have some things to kind of take care of here, right? Like, for example, what is this? What is the crazy R? So that's going to be a process we're going to need to find every single time we do one of these is what's crazy R. And crazy R in this circumstance is just the hypotenuse of this triangle. So the square root of z squared plus d over 2 squared, right? And then lastly, we want to kind of get rid of this cosine theta because we're just introducing theta as something to deal with, right? Thank you for the alert, Gauss. I'll be here when you want to come back. And this cosine theta is, we can describe it in terms of things that we know like d over 2 and z. No, my chalk. Okay. I caught the chalk. So cosine theta is just going to equal z over crazy r. Or we can rewrite that, of course, as z over the square root of z squared plus d over 2 squared. Okay? Easy breezy. Now, that means we can rewrite our total E field as just a combination of all of these things plugged in. And we get the following. 1 over 4 pi epsilon naught times 2 qz divided by z squared plus d over 2, that quantity to the 3/2, all All in the z direction. Delicious. So this is how it is. This is what we do when we want to find electric fields, okay? And you can change this to whatever. You can consider one charge, you can consider many charges, you can do all sorts of stuff. But these are for just point charges, right? We can do this with point charges. Nice. Okay, so we can do this by setting, by just considering point charges, but nature is never that nice to us, right? We don't see just point charges. What is a point charge? A point charge is a charge that exists at with zero dimension, right? It does not have a length, does not have a width or a height. It exists in zero dimensions, okay? And we can do this basically by just, taking a particle and just saying, ignore the dimensions of it, right? And what are we left with?
Always has problems with the E and M lady.
It's like the lunch lady, except she dishes out Gauss's law. Equally as adored. Okay. Let's talk about something a little bit more complicated, though. Yes, the point charge has zero dimensions. Nature doesn't ever really give us anything with zero dimensions, though, right? And we can talk about a point charge as in like a point, but eventually we need to ascribe stuff that has dimensions, right? Like a Tesla coil. We talked about having a bunch of surface charges, right? And then shocking us. And we need to make use of those dimensions. So we can consider the electric field due to any shape with the following equation. Equals 1 over 4 pi epsilon naught, not set to 0, not set to 1. The integral of 1 over crazy r squared times crazy r hat dq. Now what does this mean? Well, let's just have some shape. And in that shape, we're going to take out an infinitesimally small chunk. Why do I say infinitesimally small chunk? What's significant about it being infinitesimally small? Well, it's significant because it's dq. This is dq. The infinitesimally small, this is a charged surface. It's a charged surface. And on this charged surface, we're going to take out an infinitesimally small chunk of that charged surface. And that charge, disqualified, or Dairy Queen. One of the two. I love Dairy Queen. Yeah, so if this is a charged surface, if we take out an infinitesimally small chunk of it, then we have an infinitesimally small charge, a point charge. So we're going to take that point. We know how to handle a point charge, right? We can write this as our point charge formula, which is just some variation of the electric field that we had before, right? So we can have some point charge here, and then we're going to take that point charge and we're going to use this integration thing to integrate it up into the entire charge. However, as most people find out, integrating a small charge into a large charge doesn't really make sense because we normally think of integration over dimensions. Okay, so the relationships that we're going to be considering now is going to be a uniform charge density. We need uniform charge densities or else we can't just integrate it into the full shape. We'll have to split it up into different integration things. It could be very complicated. So instead, we're just going to consider uniform charge densities, and we have 3 of them. Lambda, which is going to be the total charge over the total length, because it is, in fact, a line density. I forgot the D in the notes. Jeepers, cats. On that line density. What's the English translation of what I just said? That's funny. Yes. So, let me just reiterate it one more time in case people do need it reiterated. We're going to have a surface, some odd shape, full of with a uniform charge. Okay? We're going to take an infinitesimally small piece of it to get an infinitesimally small point charge. That point charge is what we want to, that point charge is what we're going to evaluate, but by evaluating it, we're going to integrate it into the entire solid. Okay? It's all going to be done in one shot. So yes, this is the first dimension. This is linear. Next up, so you could think of a line charge, right? We'll do a line charge problem in a second. Next up is an area. an area charge density. So we could have total charge over total area, or an infinitesimally small charge over an infinitesimally small area. So notice that if this was an actual surface, we'd have a two-dimensional area with an infinitesimally small piece of that two-dimensional area, dA. Now, last up is our third dimension, volume. The total charge over the total volume is equal to dq over d. He uses tau. I get it. dv is messy for this. Ko Razek, thank you for the follow. Welcome to the channel. dt tau, is going to be our volume density. Each of these is going to have an associated integral. Let's make a little bit more room. Our shape has morphed into a different arbitrary shape. Our linear charge density is going to have the following electric field. That's still just not enough room. So we'll have to do a different, we'll have to write it down here or something. The linear charge density is going to have an integral that looks like this. E, which is a function of the radius, is equal to 1 over 4 pi epsilon naught times the integral now of the charge density divided by crazy r squared multiplied by r hat times dl prime. So now we have basically said, hey, we have this dq here. I don't know what to do with dq. I don't know how to integrate dq into, you're stoked for this? Oh no. I don't know how to integrate dq into, you know, a solid. I don't know how to integrate that in a spatial dimension. But I do know the relationship between how much total charge exists inside of a spatial dimension. So we can say, well, hey, this dq is actually just equal to lambda dl. And that's what we do down here. We just plug in dq is equal to lambda dl. Wet nine whistle. Thank you. So, and then again, we'll have different ones associated for the different sections. We'll have a surface charge density, q over, oh wait, this is just an equal, excuse me. Surface charge density, q over, oh, I wrote that already. That's why I did the arrow, so I could do the E field. The E field associated with the surface charge density is 1 over 4 pi epsilon naught integral of sigma surface charge density divided by crazy r squared r hat dA prime. I don't need to write the third one. You guys know what's going to happen. It's going to be the volume density, dot, dot, dot. Okay? We don't need to write it. You guys know what's going to happen. So, now we can take what we knew about point particles, like, right? Like we know point particle stuff. We did that. It's good. It's good. It's grand, even. Now we can take that and establish the electric field away from a solid by using our method of charges on a surface. So let's do an easier one to start with. I mean, actually, this was probably the hardest one. Example 2. They're just sloppy. I mean, they do get harder, obviously, but this is not, as you're going to see here, it's really just not that pretty. Okay.
Drink, mister.
I did. I drank. Okay. So example 2. Find the E field, a distance z above the midpoint of a straight line segment of r of length 2l. So let's bring our picture back. We have, you know, a point of interest, some length z above, but this time instead of a charge, several charges, we have a charge density, a line. And on this side we have, it's 2L, so we have L here and L here. And so now instead of we can't just draw like a point, right? Or say, or say, you know, that there's, you know, we can take this Q from here and go that way and a Q from here. No, you can't do that. So instead what we're going to do is pick an arbitrary spot, just like this. An arbitrary spot on the line charge density and call it dx, where this distance here from the origin is x, okay? So we're going to take some distance x. So this point on the x-axis is x, and we're going to take the infinitesimal small part around it, and then we're going to treat that infinitesimal small part like, you guessed it, a point charge. Because we know how to handle point charges, right? So we know how to handle point charges. So we're going to treat this infinitesimally small part as a point charge, and then integrate it to the full line. So let's write down a bunch of stuff that we're going to need to know. Like, so here's our point of interest. Here's our crazy r. Ooh, actually a little too crazy. Here's our crazy r vector away from our point of interest right here. And then I think that's all we really need to know, okay? Now, let's see, we have our E field for a line charge exists right here. So we're going to need to get into that. And what is our R vector? Remember, our R vector is the point from the origin to the point of interest. So that's just going to be z hat, okay? Our R prime vector is going to be the point of origin to the charge, the source charge. So again, treating this like it is a source charge, x hat. And lastly, our dl is going to be the length of this, so that's just dx. Okay, so that's our infinitesimal small point. And now we can say our crazy r is going to be r vector minus r vector prime. And that's just going to be z hat minus x hat. Good, good. Good, 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 good. Now, oh, we have more to do. How about the magnitude of r hat? Magnitude of r vector, is again just the square root of z squared plus x squared being, you know, the distance from here to our point charge, and then our hat. Our hat, we have to rewrite it in a different way. We do know that our vector is equal to the magnitude times the direction. So the direction is equal to the magnitude divided by the vector divided by the magnitude. Vector divided by the magnitude. So this is going to be equal to z hat minus x hat divided by the square root of z squared plus x squared. Okay? This is, poor x doesn't get a hat. Did I miss an x hat? X has x hat. And they're friends. Okay. Now, can we write the E field? Where's so our structure for the E field is going to exist right here. Okay, we don't need that. So our structure for the E field exists right here. So let's write that down and then do our appropriate plugging in. And we get 1 over 4 pi epsilon naught. Okay? Times the integral from L to minus L lambda divided by z squared plus x squared times z hat minus x hat divided by the square root of z squared plus x squared, all multiplied by dx. Now, we are running a little bit. I don't want to spend the entire, it's been an hour we've been working on this, or almost an hour. So I don't want to spend the entire time working on this. So what I'm going to do is skip to the end. The rest of the derivation is in my notes. You can take a look, or in Griffiths if you want to look there. If you would like to see it from here to the final step, then we can do that in the question and answer time afterwards, okay? But if someone does have to go, or if, you know, anything like that, I don't want to keep them waiting. Let's go to the end result. Basically, this is our integral, and we want to evaluate this integral, okay? And the evaluation would follow.
That is cheating, boo.
It's not, if you would, okay, let's try again. If you would like to see me do the derivation, we can do that during the question and answer time. Tyrion, If anybody else is in a hurry, they may grab the derivation from my notes or from the book. Man. Jeez-a-loo. 2 lambda L. Everybody who doesn't know, I'm just joking. I love Tyrion, and he loves me. We're best friends.
Don't patronize, you monkey.
Oh, man. Okay, so here's the answer that you get from evaluating this integral. Okay? Now, we have one more thing to do. I promised that we would find our first Maxwell equation, so I want to make sure we get to that today. So let's keep moving, because I want to make sure we get that first Maxwell equation done. And today's been a lot more chit-chat than most of our discussion series have been. I like the chit-chat and everything, but like we've had to talk more about like what is this, what is that, instead of just like move through like the definitions of stuff. So, so field lines and flux. So again, we had that picture of the field lines that we drew around the particle at the beginning, and that's what we recognize as field lines. We can also say let's draw a dipole where we have 2 charged particles. And then they're going to have field lines that go perpendicular to the surface. Oops. Well, perpendicular. And these field lines, actually, they wouldn't go like this. They would keep wrapping around eventually, but you get the picture. Okay, so then we can talk about the direction. By convention, it always goes from positive to minus. And now, remember how I did before, how I drew the arrows very specific in length, because I said I wanted the length to be the indication of the magnitude. But this, you might think, oh, well, there's no indication of magnitude there. Wrong. The indication of the magnitude is basically how dense the lines are. That is, in the center part, the lines are much denser, so there's going to be a much stronger magnetic field there. That's how that is. My Rage Inverse. Welcome to the channel. Thank you for the follow. Okay. I'm going to use a very similar, actually, very similar analogy, NC. So then what is flux? We have to talk about what flux is. And flux is the following. This is my best indication of what flux is. But flux is how much electric field goes through a surface, right? And my favorite analogy is consider a pool with a pipe. A water in pipe. Okay, so a pipe that pumps water into the pool. So you can imagine that the pool is, full of water. And this surface right here, at the edge of the pipe, surface area, the surface at the edge of the pipe, basically how much water rushes through that surface is what we call flux. But it doesn't always, and that would be the flux of the water through the tube, but it doesn't always have to be constant, right? You can have water coming, so say if the pool is only half full, right? And the water level is right here. So water may be coming out, but it might only be half of the tube, It might only be, less than half. Or you can think of it another way. You can think of, hey, maybe it changes over time. Maybe someone is sitting there with the hose spigot or whatever it is that fills it and just slowly turning it up or down. And the water is rushing faster and faster. So over time, the amount of water going through that surface is changing, right? So flux doesn't always have to be constant. It can be changing with respect to time and everything like that. So that's what I like to think of as flux, is it's the amount of substance going through a surface, that surface being this face of the tube. And so we can think of that with electric field, right? Imagine if you just had like a box, right? And you were shooting an electric field through it, right? And it goes into the box and out of the box. So the flux would be, if you were to look at the cross-section of this field, the flux would be how much is going in, in that one side of the box, okay? Mm-hmm. Yes, Ash, yep. For the electric field in motion, yep. So,
Channel, things get a little bit.
did I miss another follow? Oh no, I got my rage. Pigaline, thank you for the follow. Welcome to the channel. So, now, let's write the formula for flux. Flux is best thought of as the integral over the surface, that surface being the object in question, that pipe with the water, or this box with the electric field. That surface of the object, the integral over that the electric field dotted with the area, okay? The infinitesimally small area, again, we want to make sure that we're going to integrate that up into the large area, the same way we did with the surface. And a dot product. A dot product is, let me just read the words from the book, the notes. Oh, hey, nice. There's maybe something there about net flux leading into divergence. Maybe. The dot product's role ensures only perpendicular components contribute. Because the flux coming into the side, we only want to talk about how much goes through in this direction of the side, right? So if you were to take a surface, right, and then we can take a normal vector from the surface, basically away from the surface, and call that n hat, okay? So the direction of that surface, we like to call it, that direction of the surface is perpendicular to the surface itself. And this dA vector is going to equal the magnitude dA, which is infinitesimally small. Makes sense, it's integration, we want to integrate that up, right? Times the unit vector n hat, which is the direction of the surface, okay? So then when we do this, we want to make sure that the only thing that survives is perpendicular. So we actually can write the magnitude E times the magnitude dA times cosine theta. Dot product should be scalar, right? So the magnitude E times the magnitude dA times cosine theta. That ensures that only
I don't understand how the hand gestures relate to the physics.
It just does, okay? You'll have to get it. I mean, don't know. I speak with my hands, and I hands with my speak. So yeah, so that we only want the perpendicular sides to get through. Very good. Density at the lines. So density of the lines through a closed surface has a large consequence, right? So the amount, if you had a closed surface, right? So let's draw something closed. And if you were to say, so it's a three-dimensional closed surface with a charge on the inside and an electric field radiating out, the density has something very specific about it that's important, right? The strength of it has something very specific about it. Okay? Think about it for a second. Okay, let's keep going. Oh yeah, so what we have the question. We had a question is, the density of the lines through a closed surface has a large consequence, namely Gauss's law. Let's consider a sphere. Gauss was the one who did this, not spheres, just sphere. Gauss was the one who did this. He basically thought this up, but basically was that if you have a charge inside a closed surface, the density of the field lines has to be relevant to something, right? I think it was Gauss who did it. The integral, 1 over 4 pi epsilon naught. At least I've been telling all of my students that Gauss did it, so I hope you did. R squared times r hat. So again, now we're going to go back to the electric field. So inside of a sphere, let's draw out here. We have a sphere with a charge in the center. The surface area of the sphere is going to be 4 pi, excuse me. Oh, we haven't done that yet. That's part of the integral, right? So we're integrating over dA. So dA has a, excuse me. dA has a, that's Cartesian coordinates. Well, you can write dA in Cartesian coordinates or polar coordinates or spherical coordinates, polar coordinates, or cylindrical coordinates. There's, in Griffiths' covers, I don't remember if it's the front or the back, it tells you each substitution to make depending on the circumstances. So we're doing a sphere, so we want spherical coordinates. So that's important to have for our dA.
Please get some water.
I have been guzzling water, guys. Are you trying to get me to go to the bathroom or something? I don't get it. I'm guzzling water. All right, so here we are. This is the dA. This is the second half of that. And now we also know that since it's a sphere, the direction of the E field will be radiating
Now explain it with entropy.
will be radiating outward. So that means with the normal force, the normal vector as well as the electric field will go the same direction. That means this cosine theta is equal to 0, which means that the entire, which cosine of theta, or cosine of 0 is 1, which means the entire electric field is contributing to the surface. So now we can do this. We can see that this cancels away with this. We actually have a double integral over two coordinates, theta and phi, and those double coordinates are basically what we call a solid angle. And what we end up getting is if you take the derivative of these two, you get 4 pi. Hence this, if you were to take the derivative of this as the area, it'd get 4 pi r squared, which is the surface area, right? Zing, zing. The r hat times r hat goes away. I guess this is dotted, excuse me. Forgot the dot. R hat dot r hat is just 1, because those are perpendicular, those are parallel. And then what do we get for this? Well, we just get q over epsilon now. So if we know the rules of superposition, now we know that we can do the same thing. If we have many charges in here, charge, 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 then they're going to all do the same thing. We talked about ET is equal to, the total electric field is equal to the sum of all the electric fields. Yada, yada. The flux, of course, then follows. The total flux is equal to the integral of, the total electric field dotted with the area. And then subsequently, this is equal to the sum of all of the charges inside the surface. Okay? So what does that mean? That means we have our Gauss's law in its original form. The total electric field dotted with the area is equal to the Q enclosed over epsilon naught. So we have gotten the Gauss's law. Okay? Fun fact, the unit of the solid angle is the steradian. Is that real? That's pretty cool. I did not know that. So we have Gauss's law, but we can do something else. We can use the divergence theorem. The divergence theorem, I guess let's get on the other board really quick. All right, the divergence theorem is basically if you have a surface integral of a dot product, then you can write it as the volume integral of the gradient of the one vector, or of the E field, of the vector, I should say, this vector, multiplied by the infinitesimal volume element. Okay? And we also know that Q enclosed, from what we did earlier, is equal to the integral of the volume integral, of the density times the infinitesimally small volume. We did this in the beginning, when we laid out all of the densities out, right? We saw that this is true. Okay? Hey, Adam. Okay, so now let's do a little trickery here. And we can basically rewrite this as, I didn't write the whole thing. Let me see if I can do it on the fly. The volume integral of the divergence of the E field, d tau, is equal to the volume integral of rho over epsilon naught times d tau. So now, if we look at these two integrals, they're the same volume integral on either side, so we can set these two things equal, and we get the divergence, or the gradient, of E, or the E field, is equal to rho epsilon naught. Differential equation, integral equation, both Gauss's law. We did it. Here's the first Gauss's law. And the differential form, of course. And the integral form would just be the other Gauss's law. But Gauss's law, very good. We're going to hold off on the next example until the next discussion because we have been going at this for a long time. So we'll hold off on the example and the steps to solving a Gauss's law problem until the next one. It's a good thing to start with. This is a good thing to end on. We get the nice differential equation. So yeah, just go ahead and read the notes if you'd like to see the next few steps. But we're basically going to come up with a nice prescription for solving Gauss's law problems and then solve them. Okay? So that's the end of the discussion period. That's the end of the discussion period. Now, let's move on to the question and answer period. And we'll just go until there's no more questions. So if you guys have a bunch of questions, we'll keep going. If you have no questions, we will stop. So if you would like to, do you have any questions that you would like to ask me about the parts of Griffiths that we covered? Basically, chapter 2 up to the first Maxwell equation, which I think takes place on, what, like 68 or something? 69? 70. Wow, it's all the way at 70. Anyways, so there it is. Episode 1, or part 1 of the discussion series stuff. I hope you, uh-oh. Oh, I did it again, didn't I? Oh man, it's so annoying. I hope you guys learned some stuff.